Good afternoon, everybody, and welcome to our next presentation here at PyCon 2019. Next up, we have Jess Shapiro speaking about Python's concurrency models. Please make her feel welcome.
Thanks for coming out today. Like you said, my name is Jess. Today we're going to be talking about 5 of Python's many different concurrency models and some of the qualities that make those different and the circumstances that you might want to use them in. So to start off, concurrency, what even is it? All of us have heard that term, but what does it mean in practice? The common explanation is that concurrency is what happens when you're doing multiple things at once. That's sort of a little bit of a simplification. Concurrency is really the idea that we can break down our programs into pieces that run independently. And we get the side benefit of when we have pieces of a program that can run independently, we can run those at the same time and get benefits like performance out of it. So concurrency then isn't just something that you turn on or off. It's something that's more qualitative. And so today we're going to be talking about some of the things that lend different qualities to different concurrency models in different circumstances and why we might want to choose each model. There are a bunch of options in Python, but today we're just going to be talking about 5. Async I coroutines, Python threads, the much scarier global interpreter lock release threads, multiprocessing, and distributed tasks using frameworks like Hadoop. So the first principle that we're going to talk about is parallelism, which is, again, what a lot of people associate with concurrency. And there are a couple core questions that we want to ask ourselves. When we do things concurrently, are they actually happening simultaneously? A good proxy for this question is, how does performance scale when you add more CPUs? If you look at the graphic on the left, or on the right rather, the left-hand model only provides concurrency that is not truly parallel. You can see that each of those tasks run independently, but none of them can run at really the same time. In comparison, the concurrency model on the right is truly parallel. You can see that as many as 3 different things are happening at once. Now, that's not to say that concurrency models that aren't parallel aren't useful. Because concurrency is the ability to break down a program into pieces, even models that don't give us true parallelism can be used to great benefit. The second principle that I want to talk about is the minimum schedulable unit, and you're going to have a lot of trouble if you Google this. Code is made up of individual semantic chunks, and depending on how we run those chunks, they behave differently. Just like an individual block of 32 bits could be a positive integer, it could be an x86 instruction, it could be a negative floating point number, or it could even be a smiley face emoji. Even when we're talking about just pure Python code, the way we execute code is really important and changes how it behaves. The minimum schedulable unit is the individual semantic unit of your code that can be decided on to be run by the scheduler, whether that's the operating system kernel or the Python interpreter, that can be completely executed and that returns control to the scheduler for it to do the next thing. The third principle I want to talk about is data sharing and isolation. And the first question of this is, how isolated is data between tasks? If I have a piece of global state that I change in one of my tasks that's a part of my program, is that global state change reflected in my other concurrent tasks? If I acquire a piece of data, and this is the classic example of my program is a bank, and I look up the bank account balance, how long does that data stay good for? Can I trust that no other task is going to modify that piece of data before I need to use it? And finally, what tools can be used to share data? In models where there's a lot of state that's shared by default, these tools are typically going to be things like locks or flags that allow us to ensure consistency, in fact, reduce the concurrency of our application. In comparison, for models that don't share data by default, these are tools that are going to allow us to move data between tasks that each of those tasks need to be aware of. So jumping into our 5 models, we're going to start with Async I coroutines. Only one coroutine runs at a time. So right off the bat, we know that in Async I/O, the concurrency model is not a parallel model. Instead, each coroutine will yield out to the event loop on a regular basis. The minimum schedulable unit is the awaitable block, and global state is consistent within each awaitable block. What does that look like? If you look at the code sample on the screen, an awaitable block could be defined as the section of code between the start of a function call or the start of a call to a coroutine and the first await statement in that coroutine, or the space between each await statement thereafter. It doesn't matter what we do in between those statements. We're not going to yield out to the event loop, and so we can be assured of data consistency. We might make a print statement. We might sleep synchronously inside the thread. We might loop over 10,000 different times. If we don't await out, then we're still in a single block and we're still consistent. In comparison, as soon as we make an await statement or a call to another coroutine, we lose that consistency because we've yielded out to the event loop. We're in a new block that is independently scheduled. Now, the event loop in Async I/O basically receives information about the work that each coroutine needs to have done. That could be opening a file, that could be waiting a certain amount of time, or that could be writing to a network socket. The event loop will prepare that work to be done, and then once that work is ready and completed, it will re-enter the coroutine that was in process. Here is some more sample code. On the left, we have an example of two really good, well-engineered coroutines that work well together. The top method, tick up, just increments a counter that's shared between the methods every tenth of a second. And the bottom one essentially just enters, acquires the information about where the counter is at the beginning, sleeps 30 seconds asynchronously, and acquires information about where the counter is at the end. And because we tick up every tenth of a second and it's waited about 30 seconds, the counter should have incremented about 300 times. In comparison, on the right, the print and sleep sync function is very similar, but because it never yields out to the event loop, instead using the time.sleep function call, this means that the other coroutine never gets a chance to run. This is a common pitfall when we're doing things synchronously that we should be doing asynchronously. And so when we get the information about where the counter is when it starts and where the counter is when it ends, they're in the same place, which means that we aren't doing work we might need to do. But that also provides like a really good example of that data consistency within a single awaitable block. The next item is Python threads, and this is probably the most commonly used and well-known concurrency model that most of you have used before. Technically speaking, only one Python thread runs at a time due to the global interpreter lock, but that can often seem to be other than the case because Python releases that global interpreter lock during blocking I/O operations and sleeps. The minimum schedulable unit is the Python bytecode, which is what Python compiles your expressions down into when it runs them. And global state is consistent within a single bytecode, but that doesn't really provide any strong guarantees. If you look at the 4 statements on the left hand of the screen, which of those is a single bytecode operation? One of them is, I promise. Which of you think it is the first one? Just raise your hand. What, the second one? The third one? And the fourth one? Okay, so we got some pretty even distribution here. In fact, it is the second one, but the point of this exercise isn't really to find the right answer. It's to kind of inform you that you shouldn't rely on Python bytecode consistency. Instead, use primitives that are designed to allow you to work concurrently. The bytecode consistency is mainly there for the Python interpreter itself. Now, when we're talking about scheduling Python threads, it's sort of a combination of the Python interpreter, which decides both when to attempt to acquire the global interpreter lock and when to release it. But when we're attempting to acquire the lock from multiple threads, the operating system kernel is actually the entity that decides which thread gets a hold of it. You can see in the graphic on the right that as we move through time, shared state is mutated for all threads simultaneously, and that it happens during a single schedulable unit. And we have some sample code on the left. Again, a very well-behaved threaded program. We have a really simple method here that increments a counter 1,000,000 times, and we run it 8 times concurrently. At the end of it, as we expect, the counter is up to 8 million. On the right hand, we take a little bit more of a cavalier approach. We don't gain a lock before incrementing that counter, and rather than the 8 million times we usually expect, we only get about 3.5 million. This is a really simple thing to do, you would think, but it really shows that you can't rely on any sort of external guarantees other than primitives that are designed for allowing you to be concurrent. Talking about releasing the global interpreter lock, here there be dragons. Generally, when we're talking about releasing the GIL, what we're going to be doing is calling out into another language like C or Rust or Go or really any other language that isn't C, and doing some really performance-intensive work there. That allows us to both use optimized machine instructions, and because we're not interacting with a Python interpreter, we can safely allow multiple threads to run concurrently without putting any of the Python data at risk. Global state in a GIL released thread is entirely shared and also entirely unreliable, so we want to avoid using that shared state as much as we can. Instead, when we're ready to communicate, reacquiring the global interpreter lock and passing the data back into Python where it can be passed around safely. GIL release threads are entirely scheduled by the operating system, and we have some sample code here. This is not Python. This is a Python function implemented using C that receives a string as an argument that uses the pybegin allow threads macro to release the global interpreter lock, does something very computationally intense with that input string, and then reacquires the global interpreter lock before passing the data back into the application. What you really want to be using code like this for is implementing, maybe you have a core algorithm at the heart of your library or application that's really intensive. If you implement just that tiny bit in a compiled optimized language like Rust or Go or C, and then use Python to really provide a robust API to that algorithm, you can get a lot of performance gain that way, but it can be really hazardous, and you want to be very careful to ensure that you stay away from touching the Python interpreter itself while you do that. That brings us to multiprocessing, which is, even though it seems like we've been getting more and more scary as we go through this, multiprocessing actually becomes very comfortable again. Multiprocessing allows us to run Python code in parallel, truly simultaneously, with global state that we don't have to worry about. Essentially what happens when we spawn a child process is that the entire state of our Python application is copied over into that new process. And once it's copied over, we can make changes to global variables however we want, and they don't affect the state of the parent. If we change state in the child, it doesn't affect the state of the parent, and if we change state in the parent, it doesn't affect the state of the child. So it's very safe, very easy to use. You can see in the graphic that each child inherits its state from its parent, but from then on sort of evolves independently in doing its own thing, and those states are not commingled. And the code sample for that is, of course, very simple. When we make the os.fork system call, the return value informs us about whether we are the child or the parent, with the processes being otherwise identical. If we're in the parent, we're going to print that shared variable that we have originally, modify it, print it again, no worries, because the child has separated its address space. We can modify that variable as much as we want without interfering with what the child is doing. If we start out on the child, similarly, we can print that variable, modify it, do whatever we want without worrying about interfering with the parent process. That brings us to distributed tasks. This is often using a framework like Hadoop and an orchestrator like Yarn. We're going to talk about one particular distributed task model in particular, specifically Hadoop MapReduce streaming jobs. Often the minimal schedulable unit is the entire application being run for some subset of the data we want to work with. So for example, if I have a 100 terabyte chunk of data that I need to process through and 100 CPUs, then the orchestrator will take care of splitting out that 100 terabytes of data into 1 terabyte chunks that can easily and conveniently be sent to each CPU to be worked with. Each of those execution units or compute nodes or whatever the framework you're working with calls them will often execute a process that's entirely independent from all the other execution units, just on the chunk of data that it receives. Notably, using this concurrency model, there can be a lot of overhead. And so you really want to be sure that you have big data in the ranges of hundreds of gigabytes to hundreds of terabytes to hundreds of the next thing before starting to use a model like this. It's often the case that for smaller pieces of data, you can actually incur a performance cost by going to a framework like this before you're really ready for it. And here's a code sample for a very simple job that just reads the lines of input that it receives from the orchestrator, performs a process on each one, for example, maybe converting a log line from a comma-separated format into a structured JSON format, and then prints the result of that line back to standard out. In this case, the orchestrator feeds the data in line by line on standard in and retrieves the process data from standard out. You can see clearly that this program doesn't even really know about the framework it's running on, and it's very safe and very simple. Often when using a framework like MapReduce, a number of jobs like this will be chained together to do things like count the number of a particular word in a file. We might have a data set that's too large for an individual node to handle, but we describe the problem in terms of a series of steps that lead towards a solution that means we can separate the data out. So when do we want to use each of these models? Async I/O is fantastic when our performance is bound by us doing I/O operations like network requests or reading or writing files, rather than CPU or compute bound, like doing lots of complicated math. Because async I/O isn't a parallel concurrency model, it doesn't allow us to gain performance it doesn't allow us to gain CPU performance specifically from implementing it. Async I/O is especially great if you're starting a new code base from scratch without needing to integrate existing legacy code. This is the case because if you have legacy code that you need to use, you'll often find yourself adding threading anyway, and your threading interferes with the consistency and safety guarantees that really are the hallmark of async I/O in the first place. Threads are great when you need preemptive multitasking, that is, when you need tasks to be able to interrupt other tasks. When you need to integrate existing synchronous code that explicitly waits for operations to complete from the operating system. When you need fine-grained concurrency, like tasks working together with each other simultaneously without yielding out to an event loop. Or when you're writing optimized C or Rust or Go code and really need an API to glue the pieces of that optimized code together. Ideally, again, you want to keep the scope of that compiled code as small as possible so you can take advantage of the safety and consistency guarantees that Python gives you. Processes are great if you have parallel tasks that don't need substantial inter-task communication. Because processes don't share memory space between them, it becomes much harder to share data when you need to. You'll typically implement shared data using things like pipes or files or memory-mapped regions that are shared between processes. Processes are also great if you need full parallelism for Python code specifically. If your program is implemented in a particular way in Python already, and you can think of an easy way to split the data apart, going to a multiprocessing model can give you a really quick, really easy performance win. Using distributed tasks like Hadoop are wonderful if you have a highly segmentable and distributable workload. This is the case if you have a lot of data, if the data doesn't depend on other parts of the data a lot, if your need for shared state is minimal, because the overhead of communicating between compute nodes in the network becomes even greater than the overhead of communicating between multiple processes on the same system. And when you have a large enough workload to overcome the performance overhead of an orchestrator that splits your data apart. I'd like to acknowledge Alison Kapter and Chris Fenner for reviewing these slides for me, my various other friends and mentors for their belief and support, carbon.now.sh for the ability to create nice high-quality code snippet images, Mazarin on Market Street in San Francisco for avocado toast and espresso. Very important. And all of you for coming out to this talk. If you'd like to contact me, there's some information on the screen, or I will be available for questions now.
So yes, if anyone has questions, there are microphones in the aisles there. Please phrase your questions as questions. We do not need comments or stories at this point. Are there any people with questions? Guess not. Please thank Jess again. We have it. No. Sorry, we do have a question.
Is this on? Can you hear me? I went from programming in a code base that used threads to programming in a code base that used async I/O by switching code bases and switching jobs. Are there any successful migrations between the different paradigms that you've outlined?
Yeah, so it's often the case that you're able to switch from between processes and threads very easily, or relatively easily, because they're actually based on the same underlying Unix fundamentals. When you look at the way threads and processes interact with the operating system, they're actually treated in very similar ways except for the difference in memory mapping. And so if you're able to identify the points where there might be data conflicts, then switching from one to the other can be done very successfully. Switching from threads to async I/O is a lot harder because when you're running multiple threads, you're typically using blocking operations. And that sort of defeats the purpose of using async I/O. Because you're not yielding out to the event loop, other coroutines aren't able to run.
Well, thanks for the talk. I've got a question about multiprocessing. I ran into a project recently where we wanted to share more state than there was potentially addressable space in RAM. Is there anything that we can do in a situation where we run into that annoying error where it can't send enough memory across?
Okay, so if I'm understanding the question correctly, you've got a situation where you're already using multiprocessing to great effect, but you're finding that the amount of state that you need to share between your individual tasks is maybe greater than multiprocessing is really designed for. So in that case, if you have a large enough data set, then you could look at moving to a distributed compute model. If you have a smaller data set but just need to share data between tasks more easily, then your typical recourse is going to be go out to the file system to do it. And that can either be an actual disk-backed file, or in Unix you can have memory-backed files that are high performance and allow you to communicate easily.
Thanks.
My question is, will you be posting your slides somewhere?
Eventually. I'm not sure where. I will figure that out and get back to you.
Are there any more questions? Thank you again, Jess.